Hello everyone, welcome to a new video. In the previous video, we discussed about how does a computer really turns on and what is bootloader in that booting process. So in this video, we are going to write a small portion of bootloader and also simulate it using an emulator. So let's start the video. First of all, we need to set up two things. One is the assembler for assembly file, and the second thing is we need to download a emulator called QEMU to simulate the booting process. So let's type the commands for it. For NASM installation of NASM is a assembler. So for installing that, we need to type sudo apt install NASM. So I already have installed it, so it is easy for me. And also for the emulator, just type it emu uh, system x86, and that is all we need for the development environment. Now I'm gonna first clear the screen, and then I'm gonna make a directory where we will be working on the project. Let's go inside of it, and first of all I will open a VS Code because I want to code in VS Code. I don't like Nano or Vim. So let's open VS Code. Now that we have opened the VS Code, I'm gonna make two directory over here. The first one will be for our raw binary file, and the second is for the source file. So we do that. I'm gonna name it source and another for binary. Okay, and inside this source, we will have the assembly file, that is bootloader.asm. Okay. Okay. So before we start, I want you guys to understand this. In real mode, we use segmentation, right? In an segmentation allows us to address memory up to 1 MB using just 16 bits. That is my main goal for the viewers to understand how that is possible. So I have small notes in my OneNote. So first of all, I will like to explain that before we start to code. That's why it becomes much clear to you when you see the coding instructions. Okay. So so let me start from the memory problem, because 16 bit can address up to 16 kilo byte 64 kilobytes of memory. We were low on address, so Intel used two registers to form a new address where it can address up to 20 bits. That is the uh, main idea. So the memory is divided into segments, and each segments is 64 kilobyte wide, and also we have a offset which also can go anywhere in those segments. That means we can reach anywhere in segments using that offset. So the main formula for this is segment number into 16 plus offset. Okay. So why multiply by 16? Let me explain this first. So this is a number 10, and the binary representation of this number will be 0 1 0 1 0. And if we left shift this number only one time, this is what you will get. And this, if you convert binary to decimal, this will be 20. That means shifting one bit means it equals to multiplying by 2. That means multiplying 2 4 times. That means multiplying by 16 equals to shifting bit by 4 bit. That means we added 4 bits to the right side of the binary. That means 16 plus 4 equals to 20. That means with segmentation trick, we are able to address up to 2 to the power of 20. That means 1 MB of address space. That's the whole logic over here, okay? And one more thing, for the segmentation, we have a special register. For the code segment, we have code segment register. For the stack, we have stack segment register. For the data, we have data segment register. And for the extra segment, for the string operation, we have ES, okay? And the offset corresponding to this segment is instruction pointer. That means code segment offset is instruction pointer and stack segment is stack pointer. This data segment is source index and extra segment offset is data index, which we will be using, okay? And I think that is it. Also, one thing I want you guys to understand is that we, as a programmer, cannot change the value of code segment. This can only be done by the BIOS. Also, same applies to instruction pointer as well. And segment register is 16-bit. Also, the offset register is also 16-bit. And that is for later. Okay. So now let's go to the coding first. So as I have told you, we have to address everything in 16 bits. So I will first tell the assembler to calculate address and the data using only 16 bits. So this is the assembler directives for the assembler so that he or she can understand that. And then, uh, as I have told you in the previous video, our bootloader will be starting from 0x7C00 address. So that's why I will be using a org direction directive so that assembler understand to uh, calculate symbol address and function address uh, related related to not relative to this address. Okay. 0x7C00. Now, uh, let's clear the interrupt and let's start from here. Okay. So as I have told you, the code segment is already set by the BIOS, and the we have to handle uh, stack segment, extra segment, and data segment. But we have told the assembler that the bootloader starts at 0x7C00. That means we can make all those three segments equals to 0 and only work with segment. And with that, we will be able to address all of the code segment, or you know what I'm talking about, right? So that's the plan. So let's make those segment 0 first. And so that's why first, so to make it 0, I will move AX to contain the value of 0. And then uh, first of all, let's make data segment equals to AX, and then stack segment equals to AX, and then extra segment equals to JX. Okay, so if any one of you guys are wondering, why can't we just do move ES 0x00? Because if you see the hard instruction set, this is not just possible. That's the simple explanation that I can just give you. Okay, so we have to use a register uh, for to change a data segment or any segment. So that's it. So I will just remove it. Now, what we can do is we can set the stack pointer to point to 0x7C00 address. Now, another thing you might be asking is that the code also starts from this address, okay? And the stack pointer also start from this address. So doesn't that mean that they might possibly overlap each other? So the answer is no, they won't overlap because the code grows upwards, and stack grows downward. I have also a diagram in my notes for that. So let me see you. So okay, our code starts from 7C00 and it grows upward, and our stack grows downward. Okay, and every time you push in the stack pointer decreases by 2 bytes, because we are dealing with 16 byte, and then it will write to that address after decreasing. Okay, and every time you pop, first of all we will read 2 bytes from those address, from that word specifically, and then we will subtract it so that it retains the original position. And that is the whole concept of stack. So okay, that is that means we have implemented what we need to implement. And so I will set up the interrupt here again. And as you remember in the previous video, the boot signature, so at the last of the bootloader there will be a boot signature of 16 bits. So that means I will define a word for, and the boot signature was AA55, right? Okay. And if you also remember, I told you there will be some instruction, and after instruction there will be a garbage value, but we don't want a garbage value, so we will pad that bytes with 0. So that is what I will do in this using this command times directive data directive times 510 minus a single dollar sign. Let me first write the code, then I will explain it to you. What does that mean? And define by and 0. Okay. So what does this single dollar sign and this double dollar sign mean? Though, so the single dollar sign gives the instruction pointer address at this value. Okay, at this line 15. Whenever the assembler will calculate the ops address, this will be the first dollar sign value, and this double dollar sign is the value of the first instruction, where the first instruction will be, in our case the first instruction will be at 7C00. So this while calculating the symbol table, this will be filled up with 7C00. Also I have it on my notes so that you can see it visually. So you can see that this whole code section is 510 bytes, right? Because 511 and 512 is occupied by boot signature. So all of this is 510, and this corresponds to this times direction directive address at this instruction pointer address. And this double dollar sign corresponds to uh, this first instruction, that means 0x7C00, and that means if we subtract this whole from this small portion, we will get the bytes we need to pad. That's the concept. Okay, now that is what we will be doing in this video. That is a complete bootloader, but as I have told you, we will simulate it in a emulator. That's why we need to do something so that we can see the result visually. And that's why I'm gonna print to a screen and show you guys using a emulator, so that's we know that this bootloader program is working correctly. Okay, so that's it. So let me first define a string. Okay, let me create a label string, and then define byte. This is a test that we need, and at the last we will also add a null terminator, so that says like we have reached the end of the string and we can just uh, go away from it. Okay, and now um so let me create a print label. Before creating a print label, uh, let me explain you like let me explain interrupt that we will be using. So we will be using 0x10. That is a hardware, not a hardware, that is a software interrupt given by BIOS to us so that we can print to the screen. And for that, uh, AH, okay, AH value is 0x0e, that means that we will be printing to screen. And AL, this is the value. The AL will contain the value that we need to print to the screen. Value we need to print. So that is it. So let me comment it first. Now I'm going to move the first byte of the string to the source index. Move first byte of the string to the source index. We are doing this because I am going to increment the source index, and we are gonna find the null terminator in this dot print label. That's why I'm moving the first byte to the source index. So inside of here, what I'm gonna do is first move the content what is inside the first address of the string, and then I'm gonna not first, sorry, of the source index, because source index and string are at equal address now. Now I'm gonna increment the source index over here, and then we are going to compare. Okay, we are going to compare if AL equals to 0 or not. If it is equals to 0, then we can know that uh, uh, we have reached the null terminator. So if it equals to 0, then it will set the 0 flag. That means if it is equals, then we will jump to the done label. Okay, so let me write a label over here, and inside the done label we will just jump to the current address, nothing more. And if it is not equal, that means there is a character over there. That means first of all what we will do is fill the AH with 0e. That means move AH with 0x0e, and then we will call the interrupt so that it can print to the screen 0x10. And uh, then we will jump again back to the dot print, and this should fix it. Okay, now let me check it if we have made any mistake over here with 16 0x7c00. Okay, this looks fine. Okay, now I'm gonna save it, and now we are going to WSL so that we can recompile it. Okay, so for compiling we are going to use NASM. So NASM forwards to a binary file. Okay, so source, source bootloader dot asm, and to an file and it binary, and we want to name it is boot dot bin. It is a raw binary file, no header file. Normally in a execute in a file in a Linux file, in a executable Linux file, it has header so that the loader can read it and um, do his do his things properly. But we want a raw binary file because we don't have any loader or operating system involved in it. So so that is what we're going to do. Okay, now to simulate in the printing, we are going to use emulator called QEMU that we already installed. So I'm gonna write the command over here, and the command is very long, so I'm gonna use my notes. And so the command goes like QEMU um, system x6 64 dash drive uh, format equals to raw and file equals to, it is in yeah, binary dot boot dot bin. So if we have done everything right, this should print what we intend to print in the screen. Okay, so you can clearly see that it has said that booting from hard disk, and this is the test that we need to print, and that is what we wanted to print. So this is for this video. In the next video, we are going to step one step ahead and implement a global descriptor table, and we are going to learn something more that we need to to go to protected mode, 32-bit mode, and also eventually we need to go to long mode. So we also need to implement global descriptors table. So that means in the next video I'm gonna describe a lot about global descriptor table. That way you can easily grasp what I'm talking about, and it is easier for us to code the next future bootloader. Thank you for watching in the video. I hope you are guys are doing good. Have a good night or a good day, and thank you.